Okay, let's start recording. Okay, so today talk about surface tension. Surface tension is not in many applications. It's not very significant. Usually in industry application, pressure is more significant effect in fluids. But sometimes when you deal with a small scale fluid mechanic problem, very small, tiny, then the surface tension effect will be relatively more obvious. Okay, so I like to spend a class on surface tension, so that you at least keep in mind there might be a surface tension effect in the future application when you encounter. Okay, so what is surface tension? I read the textbook. I don't see a complete sentence talk about surface tension. Okay, the best sentence I find is on page 45 above equation 2.22. It says, many experiments have shown that surface of liquid behave like a stretched membrane. The material property that characterize this behavior is surface tension. Okay, that's the sentence in the textbook. It's not too clear to me. It's just like tell me it's like a stretched membrane. Okay, it depends on application. For example, I always like to use water droplet as the example of surface tension. You see rain yesterday, right? Rain droplet. Okay, if you ever take a look at the droplet is always spherical. Did you ever see a triangular droplet? No way, right? Always sphere. Why is always sphere? You see, on the surface of that droplet, it's a membrane. Okay, the textbook, the sentence says, hey, it's a stretched membrane. Then the property on that membrane is slightly different compared to the property of water inside the droplet. Okay, on the membrane, basically it has more significant attraction forces between the water molecules. Okay, so that surface, that membrane behave a little different comparing to the regular water, basically was what it says. So what's the difference? The difference is actually there's more attraction forces between the water molecules on that membrane, on that surface. Okay, more attraction forces than the regular water molecule inside the droplet. Okay. And also surface tension not only happens in this is the surface between the water and the air, right? The water droplet. Outside is air, inside is water. So there's a membrane protecting the water. Okay. Then on the membrane, the water molecule attract to each other more. Okay. So it creates the stretched membrane. Okay. But sometimes surface tension happens between water and the solid surface also. Okay. So you see, if your water is in a container or or whatever solid cup, okay, a tube, okay, when you look at the water near the wall, you can tell me what does it look like, the water near the surface, near the solid surface. It's not a straight line near the solid surface, right? It's going up a little bit near the wall. Is that right? Is that everybody? Did you ever take a look of that? Pay a little bit attention on that? Okay, it's not a straight line reach to the wall. It's actually near the wall, it goes up a little. The water surface goes up a little bit. That's because the surface tension, the attraction force between the water molecule to the solid surface, it's even stronger than the attraction force between water molecules themselves. Okay, so basically it attracted to the wall. So it tried to accumulate it, tried to climb on the wall. Okay, so this is just example, surface tension. So let me show you a slide. I can share. I always like to use that example. I show you. It's very fun to watch. Okay. Okay. Do you see that? See my screen?
Yeah, now you can.
Yeah, okay. Let me do it's a PowerPoint. I can do slideshow, right? Can I? I'm trying to. Okay, yeah, here we go. Okay, so, okay, this is the water air surface tension. I just talk about this as a droplet, right? You see, this is the dark blue line is the water surface, okay? So it says surface area minimization. So it's the surface area try to minimize. What does that mean? Okay, results in smoothest shape it can. Smooth shape has the smallest surface area. Okay, so that makes sense because if it's an enclosure, it make a sphere. Then the surface, it intended to go, to a smaller surface area. Okay, so in other words, it basically just says the molecule, molecule on the membrane surface, on the water surface, they have more attraction to each other than the molecule inside the fluid. Okay, I think the drawing shows two molecules. One is inside the fluid. Okay, look at this. There's billions of molecules there, right? So each molecule apply force to each other, attraction force to each other, right? That's what's the Newton's law, right? So all the mass will have force to each other, okay? So all the molecules attract to each other. So basically there are billions of molecules there. So for each molecule, it's statistically balanced, the force. The force is statistically balanced on each molecule because you have 10 million molecules next to you. So it's evenly distributed. Does that make sense? So inside the liquid, it's kind of like peaceful, okay? Peaceful, harmonic. Okay, so although there are trillions of molecules there, but they are kind of like it's peaceful together, okay? Because on each molecule, the attraction force from the neighbors are balanced, okay? Now let's look at the surface. Okay, that surface molecule. Okay, surface molecule, the difference is the bottom half, it's water, and the top, the molecule exposed to air. Okay, so I guess the drawing out here, so what's the difference between this molecule and that molecule? The force balance. You see, you have all the forces from downward because they are all particles, molecules below it, right? So pull it down. So what about on top of it? There's no molecule. Okay, there's no molecule on top of it, top of the molecule. So there's no attraction force from the top. Okay, no pulling force from the top. So only pulling force from the bottom. So in the bottom, the more molecule is trying to pull this surface molecule down. Is that right? It's just like the gravity, okay? Just like you have a weight, your gravity always going downward because you have an imbalanced force. As gravity always go down. So yourself will goes downward, right? That's why you're standing on the surface of the Earth, right? So what happened to this surface molecule? Now it's imbalanced, right? You had a statics, right? It's imbalanced the force. All the forces are trying to pull this molecule down. Okay, but this molecule is stubborn. I don't want to go down. I want to be on the surface. I'm over you. I'm oversee you. I like that. I'm higher. Okay. So what this molecule do to make himself can stand on top of rest of the pairs? There must be some magical force to make it stand on the surface, right? Okay, what is that magic force? That's surface tension. Let me show you the next slide. Why can oh, here we go. Okay. I want you to take a look, see what's the relation between these two guys and the surface tension, the molecule we're talking about. Okay, think about the body, the guy is the molecule. Okay. He's doing rings, right? So each of the ring is a neighbor molecule. Okay. He has exactly like the surface molecule. He has the gravity pulling him down. Okay. He doesn't want to go down. So how many of you can do this guy, the top guy? Which country he's from? I see a flag here. Is that Italy or France? I don't remember those flags. Looks like Italy to me. Okay, you know, I watch soccer a little bit. You know. Okay, so how many of you can do this guy, the top? How many of you can do bottom? Well, first of all, I can do bottom, this guy. If you help me put me on there, I can hold it for a couple of seconds. Sure, I can do it. I think most of you can do it. You know, you don't have to go there by yourself. You know, if somebody help, you know. Okay, but I'm 100% sure I cannot do this. Okay, I think probably a handful of people in the world can do this, right? Yeah, you know, at least you have to train, you know, in that field, you know. Okay. So the difference say the bottom guys I can do, the top guy I cannot do. Okay, but the same thing, right? You know, they have two rings. Okay, so what I do is I move my rings close to me, my neighbor molecule. Okay, I can spend less force. I can use less force to sustain myself against the gravity. Okay, you see my point? That's what exactly God makes the surface molecule do. They attract to each other more. They get close to each other on the surface. You have to prevent the surface from break. You have to go closer to each other. The molecule on the surface definitely is more close to each other than the regular molecules inside the surface. Okay, so if you get closer to each other, the attraction force from each other can support yourself from falling down into the water. Okay, so why are the molecules so smart? They go close to each other. I know this seems like they took fluid mechanics class. I don't know why. That's what God makes a word, how it works. Okay. Okay, that makes sense. That's why the surface trying to minimize themselves, minimize the surface area so the molecule get closer to each other, right? Then the surface is minimized, then it will force the enclosure. If it's enclosure, spherical, that's the smallest area. Okay, that's why you always see a perfect droplet like that. It's round, never triangular, never like a cone. Okay, and the force are evenly distributed on the surface if you make it around. Okay, so that's just basically, you see, it's a perfect water droplet, always spherical. Okay. Is that understandable? It's not really theoretical, like mathematical. It's just trying to explain this phenomenon. Okay. My question is this: do you see a very, very large water droplet? Can the size of droplet be very big? Did you see a 1 foot diameter water droplet from the sky? Dropping from the sky? Why not? Let me stop sharing. I think that's the end of the slides. Okay. Why not?
Because the membrane can only hold so much weight.
That's right. That's a property. That's so-called surface tension. Okay, that's a value. That's a property of the fluid. So that force can only sustain a certain amount of You know, the maximum you can sustain certain amount of force. Okay, so if it's too big, then you know you can't hold anymore. Okay, so let's introduce that equation. Let me share my whiteboard. So we need to know that our second equation of the semester. Okay, here we go. It's our whiteboard. Okay, now we're going to continue the lecture here. Surface tension. Surface tension has a equation. Actually, surface tension equals to the equation 2.22, force along an interface divided by the length of the interface. Okay, what does that mean? It's not very clear. I think, again, I think the explanation on the textbook on this topic is not really very clear. So it's basically, what do you mean by interface, right? So again, let's use water droplet example. So if the water droplet breaks, okay, it must break the surface, right? The surface will have a break line. Okay. Yes.
Can you read the formula for surface tension again?
Oh, it is just equation 2.22 on textbook. So it is the force along an interface divided by the length of the interface.
Okay.
Okay, I'm sort of bear with my writing. You probably sometimes we need to check the textbook for the equation because my screen is vertical. Okay, so I write on a vertical computer screen. It's kind of difficult, you know, for me to write on it. So sometimes my handwriting is not that clear. Good, if you're not clear, just ask me. Okay, in case later you forgot, then please check textbook also. So water droplet, when it breaks from a line. Okay, it breaks a surface, right? If you break a surface, always a line. Okay, so for example, a surface like it's broken. So it breaks from the tail line, breaking line. Okay. What the property surface tension means is if you have a force to break it, then the force divided by the length of the break line, the interface, that's the surface tension. In other words, it's how big the surface tension is, how much force you can sustain, you know, before you break the surface. Okay. So I guess that's the definition. So actually, surface tension is a property. No, you use the property basically is to calculate, if you know the length of the interface, then you can calculate the force this surface can sustain. Okay, can hold. Okay, I think I want you to remember some property. For example, the water. The surface tension of water is 0.073. Imagine what is the unit? Force per length, right? Newton per meter. Okay, so that's surface tension. Okay, the unit. And I want you to remember this. Some of the common property, please remember that's water surface tension 0.073. Density of water. What is the density of water?
1.
No. Plus, you need to have the unit. What is the density of water? Anybody? Hmm?
1,000 kilograms per meter cubed.
That's right. 1,000 kilograms per cubic meter cube, right? Those things are easy to memorize. So just remember. So what is 1 kilogram per cubic meter? What density is that? I remember 1,000 for water. Also, I remember 1 kilogram per meter cube. What is that? What material is that? With just 1,000th of density of water.
Air?
Yeah, right? Air is a close one. Maybe not exactly 1.1, maybe 1.12, maybe 1.2. Okay, but it's close to 1, right? Yeah. So Something easy to remember, just remember. Okay, let's review something. See, I want you to remember the unit here, Newton per meter. Do you remember any property Newton per meter square? What is that? Newton per meter square. What kind of property?
That's volume.
Huh? No,
Isn't that volume with time?
Newton per meter square. What kind of things is Newton per meter square? Is that force? No, force is Newton, right? What is Newton per area? Force per area.
Surface pressure.
Surface what?
Pressure.
Yeah, pressure is, right? What else? And something recently we talked about shear stress.
Shear stress.
Right? Shear stress also Newton per meter square, right? Remember you had a quiz, right, last time to calculate shear stress based on the force, right, divided by area. Okay, right? Okay. So if one is tangential, it's kind of like a pressure is normal, right? Normal force per area. Shear is tangential, horizontal, okay? Force per area, okay? So what is Newton per cubic meter? Remember? I want you to remember all together. Then if you think about one, you can think about the others, all related, not related, okay? Easily memorize. What is Newton per cubic meter? Let me give you a hint. We did it in this semester. That's a new thing we taught. Anybody? Newton per cubic meter. Is it, you remember kilogram per cubic meter, right? What is a kilogram per cubic meter? You see, that's a string. I want you to all going all together. What is a kilogram per cubic meter?
Density.
Yeah, it's density, right? So what is Newton per cubic meter? Well, it's similar to density. That's what we learned this semester. We use this to represent the fluid property gamma, right? It's rho g.
It's not a specific weight, is it?
Yeah, it is specific weight. Okay, right? So remember those all together, okay? These two are related also. Usually in solid mechanics, people just use rho density for the calculate rho g. Here we use gamma. Gamma is equal to rho g. So it's easier to use just one letter instead of two letters. But the purpose is the same. It's just the property, right? For how heavy the fluid is. Okay, I'd like you to remember all those things. Right? These are the properties. Okay, look at the units. Very important. Okay. Okay. Surface tension. Okay. It's easy. Just a concept. I think this is the equation. This is the equation. So surface tension equals to the surface tension force divided by a length. Okay. The interface length. So this is the second equation in the semester. You need to look at the homework problem I assigned for chapter 2. Basically, just these two equations: the viscosity equation, shear stress viscosity equation, and the second equation is this. Okay, usually surface tension. I don't see any problem in the textbook assigned to you for you to calculate surface tension. No, it's surface tension always a property. It's always given. So this equation basically you're gonna change the form. It's actually F equals to surface tension times L. Okay, if you want to solve a problem, usually it will ask you to calculate F, or it will ask you to calculate L, maybe interface length. Okay, surface tension itself usually is a property. Okay, so that's the second equation. Let's look at an example. I guess it's very important to go through an example. Any questions before we goes to an example? Okay, so okay, let's do an example. So let's just use that water droplet example. How about that? Say we just ask how big the droplet can be. Okay, let's say, just say how large, how big a droplet can be. Come on. It's a problem. Okay. Okay. Any clue? How do we solve that? So any problem, if it's a I'll give you a trick. Any problem, if it's a surface tension problem, you need to ask yourself the question: what is the interface? What is the tear line? Okay, the break line. So for a droplet, let's say it actually can break many different places, but most likely it will break in the middle. Okay, so if it breaks, it will become two halves. Okay, is that right? Because the reason it breaks is internal pressure. Internal pressure is evenly distributed inside the droplet. Let's assume it's evenly distributed inside the droplet. So internal pressure is trying to break the droplet. Okay, so on this surface, so you have internal pressure going away from each other. Why I say it's always breaking the middle? Because the force break it, right? So what is the internal force? How the internal force is calculated? So the internal force calculated is what? Pressure. The internal pressure times the area, right? Do you remember this? Pressure times area is force. So which section has the largest area? You're breaking the middle or breaking the side? When you break in the middle, the surface area, cross-sectional area is the greatest. Is that right? Okay, that's why always close to breaking the middle. Okay. One thing I wanted to talk about the surface tension. I think I didn't mention here in the previous slides. Okay, the surface tension, you have a force here. What is the direction of the force? Okay, that's a big question. So surface tension force basically try to prevent the surface from breaking, right? From broken. So it will be the reaction between the force break it and try to prevent it from breaking, right? Okay. So the surface try to break, okay? Your surface tension force try to hold it. So it's an action reaction, okay? So by definition, the surface tension force is perpendicular to the interface and tangential to the surface where it breaks. That's the direction of the surface tension force. Very important. You have to have a different problem. You have to, it's a static problem, right? You need to draw free body diagram. You need to know what the direction of the force. Okay, listen up. Perpendicular to the tear line, the interface. Okay, see, it's a 3D geometry, right? You have a line here. Okay, let's see this example. You have a line. It's perpendicular to this line. It could be any direction. It could be perpendicular to it. Okay, that's why you need the second requirement. Perpendicular to the line and also tangential to the surface where it breaks. The surface on the interface, okay, adjacent to the interface. So in that sense, it will be, okay, this direction. Okay, see, I wrote the arrow. It's perpendicular to this line and the tangential to the surface. Okay, okay. Most of the surface tension problem seems like all 3D problems. So you need to, in your mind, in your mind, you need to know what is actually the direction. Does that make sense? So let's look at the sphere. Okay, so it breaks like this in the middle. We set it. Okay, so where is the interface, the break line? Okay, think about it's a membrane, right? It's outside the surface. You break that membrane outside surface. This is the tear line. This is a break line or interface, whatever you want to call it. Okay. That makes sense? Okay. So what is the direction of the surface tension force? Okay, so now I know my surface tension force is evenly distributed on that interface line. Okay. Let's assume it's evenly distributed, it's uniform on the line. Okay. But what is the direction? Without knowing the direction, you can't draw the free body diagram, then you cannot solve the problem. Right? You know, in my class, in front of the first quiz, you know it, right? I need the free body diagram correctly. Okay. What is the direction? Perpendicular to the interface, and the tangential to the surface that adjacent to the interface. So it's like this. Everywhere on the surface. Hey, does that make sense? The arrow I draw here, right? That's the force trying to prevent the surface from break. Okay, so this is our surface tension force in this problem. Okay. What are the forces in this problem? So how big a droplet can be? Okay, so what is this surface tension balanced to? It balanced to the internal force trying to break it. Okay, on the maximum size is just exactly at that moment. Is that on that size? Then the two forces are balanced. Okay, so we are trying to figure out a maximum situation, right? So in that maximum situation, that's exactly balanced. Okay, surface tension force and the internal force from the surface. It's difficult on the drawing on this problem. The internal force is applied the internal on the cross section. It's actually a circle area. Okay, inside. Okay, evenly distributed on the circle area. But the surface tension force is on the circumference of that circle. Okay, that makes sense, guys? Very important. It's all 3D problems here in surface tension. You need to think clear. Where are the forces applied to? Okay, you balance the surface force, which is on the circumference of the circle, surface tension force, with the internal force, which is applied on the cross section of the circle, on the entire area of the circle. Okay. Any questions, guys? Please jump in. Is that clear to everybody? So you can write that a very, very easy force balance. So surface tension force will be equals to, let's say, internal pressure. Yes.
I have a question.
Go ahead.
Can you say what F equals P times A again?
Force equals to pressure times area.
Okay, thank you.
You're welcome. You need to remember that. Force equal to pressure times area. With this class, you're going to do pressure a lot. Right now, we're going to deal with pressure and the force. Okay. So that's the equation. That's internal pressure basically here. Internal force. So this line, F sigma equals to FP, this line worth maybe 3 points out of a 20-point problem, maybe 25-point problem. at least worth 3 to 5 points, okay? Okay. Show me that based on the drawing, free body diagram, you can write down the equation. You are able to write down the equation. Use a letter on the drawing. Okay, FP, that's internal force. Okay, opposite direction with the surface tension force. One try to break, one try to hold. Okay. Is that good? So far, so good? Everybody follow me? Okay. That's the key. Then after that's a piece of cake. You can ask your intern to do it. Hey, intern, come, continue. I give you direction already. Go ahead. You're engineer, right? Okay. Next step is just expand these letters. Okay. Okay. So what is FP? I think I already wrote down here FP. That's the internal pressure times area, cross-sectional area of the circle, the area of the circle. What is the expression? Let's say D is what we want to calculate, right? How big the particle will go. What is the area in terms of D? You don't know how to calculate the circle area?
Pi over 4d squared.
Yeah. Okay. See, piece of cake. Translation. From this giant step to the following step are easy. Okay. What is surface tension force? Anybody? It's not on this page. Do you still remember?
0.073 newtons per meter.
No, that's surface tension, right? That's a property.
Right.
Well, looking at the surface tension force, what is your equation you learned today?
Okay, so it's gonna be that. Is that times the no, never mind.
What is the equation?
Surface tension times the length of the interface.
Okay, length. Okay,
No,
let's
divide.
write that letter L here before I even think about what is L. Don't frustrate yourself. Write down the step. Give yourself direction. Then sit down. Make sure this equation is right. Then sit down. Okay, what is L? Okay. Is that right? Everybody agree with this? The interface length times the surface tension is the surface tension force. Does everybody agree? Hey. Okay, everybody agree? Okay, it must be a length, right? You know? Okay, so next question is, what is the length?
Circumference of the
Circumference.
droplet.
How do you calculate the circumference based on the diameter d? What is the expression? You can write another line for this.
Just pi d.
That's pi d. You have to remember those basic equations. That's why I feel a lot of students feel frustrated with math and engineering topics, because they don't remember stuff. You know, you go through a problem, there are too many frustrations there, because every time you do something, you have to think about it and find it somewhere in the internet, in the textbook. Then, you know, too much frustration there. Then soon you will say, I don't like this topic. Okay. You know, just memorize those things. It will be very, very, very good for you. Okay.
I think it's just frustrating that they make us remember it when we have all the information in our pocket on our phone.
Yeah, but see, if you remember it quick, you know, you go through the process quickly and you feel good. Inside, you feel you achieve something, you know, you have a successful feeling that make you like a subject. Okay, to be honest with you, you have to memorize a lot of things to be good on it. Okay, so don't think everything is online. You know, I can Google everything. You know, why do I need to memorize it? Because every time you Google it, take you a minute. Okay, you get too much frustration feeling in your heart. Then you just very quickly frustrated and don't like the subject. Okay. Okay, let's see. Okay, I can copy this. Okay, let's see. Okay, great, right? Did we solve the problem? I think we did. Okay, after this is basically elementary school stuff, right? So cancel the pi, okay. Cancel a d. Is that right? So what is the question? We'll ask you to calculate the d, the maximum of the d, maximum d will be, okay, let's see. D equals, we move around the letters, 4 times sigma divided by p. Okay. Okay, that's your solution. Internal pressure sometimes is also a property, basically, a certain situation, certain temperature. Okay, so if you are given internal pressure, you should be able to calculate your diameter. Okay, it's inversely proportional to the internal pressure. If you have a greater internal pressure for that property, for that material, then your droplet will be smaller. Okay, if you have a less internal pressure of that material, then your droplet can form bigger.
Dr. Zhang,
Yes.
was this a example from the book?
I think the book is different. Book asks you to calculate the internal pressure, I guess. Here, I think this is more practical. We want to know what is the size, right?
Gotcha.
Yeah. I think to calculate size is more attractive and more applicable, you know. Is that good? Any question to this one? Okay, see, again, I looked through all the homework problem I sent you. I know what are the problems, okay? You really, the key is for any surface tension problem, you need to know the interface. You need to exactly know where the interface and how long it is. Okay, that's the key. In the, you know, without knowing the interface, how you're gonna apply the surface tension force to, right? You don't even know where to apply. How do you draw the free body diagram? Without drawing the free body diagram, how do you calculate, solve it? Okay, so very important to understand that. Okay, let me see what time. I still have half hour. Let's do the second example of. Oh, but by the way, any question, please? If you have anything not clear here, let me know. Let's talk about it.
Could you read the example statement again?
How big a droplet can be.
Thank you.
You're welcome. Okay, good. Truly, everybody understand? Okay. Let's look at another example. It's a famous one. It's called capillary effect.
Go to bed.
Yes.
Ooh, sorry.
No problem. Previous page, right? Okay. What's your question?
No question. I was talking to my dog. Sorry.
Oh, okay. No problem. Capillary effect. Okay. This is the example between the surface tension between liquid and the solid surface. I mentioned it 10 minutes ago, right? About actually on the interface between the water and the solid wall, you see a little bit rise near the wall because of the attraction is greater between the solid molecule and the liquid molecules. Okay, basically the liquid molecule is attracted to the solid surface. Okay, so what happens is if you enlarge it and make it very large, you know, a tube, okay, then near the wall is like this. I exaggerated. Actually, it's a very thin film. It's not like that. But you can see it from if you take a close look on certain near the wall. Actually, the water is rise a little bit. Okay, is that drawing clear to everybody? Okay. So, okay, so that's the surface tension force. Okay, so the surface tension force is going up. Okay, now, so let me ask you, in this application, okay, do you understand my drawing here? That's the top surface of the water, right? It's all going inside a little bit. Is that right? Hey, do you understand this drawing? Okay. Okay. Now, where is the surface tension force applied to, and what is the direction? So think about this. This going up, right? Because of the attraction from the solid wall. So it draw the water up a little bit. Okay, it pull the water up a little bit. Okay. So the surface tension force must be kind of upward. Okay. Where does it apply to? Where is the interface? I draw it here. This surface is the interface. This circle is the interface, I'm sorry. The circumference. Okay. So what is the definition of the direction of the surface tension force? Two conditions, right? What is the first one? The direction. Can you repeat what I said? So this is the process of solving surface tension problem. So the first thing I did is identify the interface. Okay, obviously this is the interface. Okay, it's a water line on the cup. Okay. Okay, this is the interface. Okay, now next step, I'm gonna apply my surface tension force on it. Okay, so what is the direction? What is the direction of the surface tension force? There are two sentences, right? Can you repeat it for me?
Was the first one tangential?
First one is perpendicular, right? Two conditions, right? If you want to start with tangential, that's fine. Tangential to what?
Tangent to the surface.
Tangent to the surface. Okay, so the surface adjacent to the interface. So the water surface down there is this surface. Okay, right? Connected to the interface. That's the water surface you're talking about. Okay, so what is the other condition?
Surface tension is perpendicular to the tear line.
That's right, perpendicular to the tear line, which is this, the interface. In this problem, it's not tear, you're not breaking or dropping particle. Basically, I use the word interface, right? Perpendicular to the interface, okay? So this is the circumference. Your arrow gonna be perpendicular to it, okay? It can be any direction perpendicular to it, right? You see? Then you tangential to the surface down here. So that's your direction of the force. Okay? It's not 100% vertical, but it depends on how thin this liquid is near the wall. Okay, the direction is almost going straight up, but it's not absolute vertical 90 degree. Okay, because it's tangential to the surface. Okay, everybody. Okay, so that would be a little bit difficult to solve this type of problem. Now you need an angle. Okay. Do you know what kind of angle it is? Between you need to make it to vertical, right? Because you're gonna balance the gravity or whatever. You with vertical components, so it's better for the calculation always. Okay. So what is angle? You need angle, right? The vertical component, F vertical. Let's say this is F surface tension force. Okay. How do you calculate the F vertical component? F equals
F cosine.
Cosine, that's right. Cosine this angle alpha. Okay. Think about what kind of angle it could be around. If you look at it, it's really tiny. Okay. Maybe 2 degree? Estimation, maybe 1 to 2 degree. Okay. So do you have a calculator? Give me a cosine 2 degree. What is the value?
Point 99939.
99939. Oh, okay. So should we say just equal to 1? Close to 1? Okay. So in that sense, we can, if it's close to 1, then we can get rid of this. Let's just assume the surface tension is vertical. Okay. See, my assumption is very strictly justified. Okay.
So what's the cutoff on assuming how close it is?
1%. Let's say this is let's say less than 1,000th difference comparing to 1, right? If the cosine angle maybe this, maybe we should not neglect. Okay. 1%. Basically, rule of thumb is 1% error. We accept. But in industry, sometimes 5% error is also acceptable. Okay. Sometimes even 10%, depending on the problem. Okay. But definitely less than 1% error is acceptable in most of the engineering application. Okay. So based on that, I think this is like a 0.01%. 0.05%-ish error. Okay. I'm slowly explaining this on this assumption here because I want you to you fully understand how to make assumption. We in our career as an engineer, we make like many different assumptions. You have to. Okay, we are not physicists, we don't care about too much of those. We care about the manufacturer, the factory, your boss, your production line, we need a product. Okay, we need to have a result. So in our career, we will make a huge amount of assumptions. Okay, but it's not whatever you want to make, you can make assumption. Every assumption you make has to be justifiable. Okay, you have to have some standard and a rule for you to be able to make assumptions. Okay, is that okay? Good. Okay. So we can assume, because this error is too little, if it's even 2 degree, 1 degree is even smaller. So if it's even 2 degree, it's so close to 1. Let's assume it's just vertical. Okay. So that make our life a little bit easier in calculation. Okay, so let's go to the next example. This page, I want to keep it here and let me draw it in the next page. Okay, so you have a straw. Let's say you have a straw you insert into the Coke cup. What? Why can't I draw something? What happened to my pen? Did I hit something today? What? Yeah, I can draw on the new page.
Did your pen die?
You see, my pen works on this page, but as soon as I go into the next page, it doesn't work. Oh, it works now. My computer is too slow now, I figured. Okay, let me erase these things. Okay. Okay, the same problem here. So you go to McDonald's, get a cup of Coke, you put a straw there. Although the straw is probably not that obvious, but if you get a smaller straw, maybe it shows more obvious. The water rise inside the tube. Okay, you have a container of liquid. Okay, you insert the straw in there, the water rises a little bit. Okay, I think it's not from the pressure because open here, open to atmosphere, and open to atmosphere also in the cup. Okay, so pressure is actually balanced. Both sides have the same pressure. It shouldn't rise for no reason. Okay, but indeed there will be some rise. Okay, if the straw is small, I will tell you how small it will need to be. Okay, if it rises like this, okay, I want you to calculate how high it will go. Due to the surface tension, the capillary effect. Okay, how do we solve this problem? How high it can go? Let's say we know the diameter. D is given. Okay, notice I give you those problems. I don't put the actual number there. We don't need to calculate it. Okay, let's just use the letter. Okay, eventually you will have an expression in terms of D, right? So with the given D value, you should be able to calculate H. Okay, that's the process. Okay. What's the first step? So if I give you this quiz as a quiz problem for the last 15 minutes, now you have to struggle to calculate it, right? What's the first step? I won't give you a quiz today. I'm just saying. Okay. So you have 15 minutes if you need to solve this problem under pressure. Okay.
Free body diagram.
That's right. Free body diagram. Okay. Good. That's a good starting point. So you focus on how to figure out how to draw a free body diagram here. So draw free body diagram, you need to identify the body. See, identify the body. For this, it's not that clear which body I'm going to draw my free body diagram on. Okay. I think I will draw this fluid on top of the surface. Okay, let's draw it again here. This is just part of the fluid. Okay. Okay. So in this fluid, what are the forces? You have a weight, W, right? Then the surface tension force on the circumference to pull it up, to balance the weight. Is that right? Is that understandable? Yeah, it's easy, right? See? If you can figure out the free body diagram, that means you fully understand the problem, okay? Then you should be able to solve problem, okay? Basically, that's the reality is there's a surface tension force pull this liquid up, okay, against the weight of the liquid, okay? It should be large enough to sustain the weight, support the weight, okay? Balance the weight, that's it. So, okay, any equation you can write down? I think it's easy. Surface tension force, balance
F
the weight.
sigma equals FP.
Equal to no FP here. Did I use W in my drawing? Look at my drawing, free body diagram. I have two letters here. F sigma,
Oh, yeah.
the weight is W. Okay, basically follow your drawing.
F sigma equals W.
That's right. That's the equation for this problem. Okay, it is based on the free body diagram, right? You draw here. You use the letter F sigma here, use the letter W here. Write down this equation. Even if you just leave it like this, turning the paper, you still get the partial points. Okay. So next is expand these two letters. What is sigma? Okay, next step. What is sigma? What is F sigma? What is the equation we learned?
Sigma times L.
Times L again. Okay, if you're not sure what is L, just write it down here. Okay, what is the W? Weight, can you calculate the weight of this chunk? Do you know the dimension? diameter is D, right? Do you know how to calculate a weight of a cylinder? See, if you cannot spit it out in 5 seconds, then it frustrates you. It becomes a difficult problem to you, right?
Is it pi d8 h? Hold on.
It's pi over 4 d squared to get the surface area, then times h to get the volume, times the
Yeah.
mass to get the weight.
That's what I meant.
This is then times the mass. This is the volume. Volume times what? Volume times density. Then times
Oh yeah, density, yes. My bad.
G, okay? See, don't make mistake on that, okay? See, and also quick. We have to figure out quickly, then stop being frustrated. Okay, is that right? Rho times volume times G. Okay, in this class, I really want you, every time you see rho and G, I don't accept it, rho and G. Okay, it should become gamma times pi. I'm sorry, it's 4D squared, right? Yeah. Okay, rho and G, gamma times volume. Remember, just remember it from today. Weight is gamma times volume. Basically, it's rho G volume, right? Gamma times volume. Make your writing a little bit easier on the paper. Can you remember this? Weight. Next time I will probably ask you, what is the weight? I want you to hear you say gamma times the volume. Gamma times the volume. Okay? You should be able to figure out the volume. Okay, if you need to spend more time on figure out the volume, then you need to really catch up, be more familiar with it. Gamma, volume. Volume is the cross-section area times the height. Okay, for pi over 4D squared times h. Okay, so left-hand side, what is L? I heard you said, but yeah, pi d, right? You said
Pi
you
d, yeah.
turn on the mic. Okay, pi d. I can tell from your lip. Okay, I guess we'll solve the problem. Do we? So we want to calculate h. H is in the right-hand side. Okay. Cancel. I like to cancel stuff, you know. Okay. So h equals 4 times sigma divided by gamma. No, I have a d here. Gamma and the d. Okay, it's too small. Can I write on top of it, repeat my solution here? H equals to 4 times sigma divided by gamma d. Okay, that's our answer. Solution for this problem. Okay, again, so I show you here. I don't have the numerical results. Okay, I just like to use the letter. It doesn't matter. You can just substitute the number there to find out the actual h. Okay, so but I want you to look at this solution a little bit here. Okay, there are the properties there, right? Sigma is a property. Gamma is a property. What is gamma?
Weight divided by volume.
Yes, right? It's rho g. It's specific weight. Weight divided by volume, that's called specific weight, right? So these two are properties, so we cannot change, right? It's a property of that liquid for the fluid, okay? Only thing is diameter, okay? Your h actually is inversely related proportional to the diameter. How high it goes is inversely proportional to the diameter. Is that right? Is that what you observe from this solution? So h is inversely proportional to diameter. So if the diameter is big, what happened to the h? It's tiny, small. Okay, that's why in a regular straw, in the Coke cup, maybe you don't see much. Okay, but if you put a tiny straw there, if your diameter is little, inversely proportional to h, so h will be bigger. Okay, that's why I mentioned in the beginning of the class, for a microstructure, microfluid, in the small scale fluid problems, the surface tension will be more significant, more noticeable. Okay, This is also an example to showing that. If your diameter is big, then your capillary rise is very small. Okay, capillary rise is very, very useful in some of the device. For example, I don't know, do you have, and if you have diabetes or you have relative has diabetes, they test the blood sugar. Okay, those test strip in you cut a little bit in your finger, they have a little bit blood coming out, right? So the test strip touched it, the water, the liquid, the blood will be sucked into the test strip. Then it can do another test, right? So why the water being sucked into it? These are the capillary tubes there, very, very tiny tubes in the tip of that material. Then because of the capillary surface tension effect, the blood will be sucked into the test strip, okay? But it has to be small, tiny, okay? If it's tiny, it's smaller, the rise will be higher, be more significant, okay? For the regular size of the application, maybe you don't see surface tension much. You know, for example, a swimming pool, the pump, you have to have a pump to pipe the flow in the pipe, right? Pump the flow in the pipe, it won't go by surface tension itself. Okay, so I guess that's what I want to convey on the surface tension topic, micro scale fluid mechanic problems. Okay, I guess that's it. I'll give you 2 examples on surface tension. I think that's sufficient. Okay, any questions?
Dr. Zhang,
Yeah.
whenever you were taking your measurement of delta H, do you measure to the top of the adhesion or to the bottom of the crest? Does it matter?
I think I think it should be the bottom of the crest, both because most of the film near the wall is tiny, very small. Okay, so most of the weight is should be starting from the bottom of the crest.
Gotcha.
Yeah, it's a good question. Any other? Is that good? Okay, so I think one more concept in chapter 2 is vapor pressure. Okay, if we're good with surface tension, let's do the last one. Vapor pressure, then nothing to calculate, versus boiling temperature. I want to put them together. You had the thermal, right? Okay, so this is the boiling process. Okay, we will use the boiling process a little bit later part of the semester on the cavitation topic. You know cavitation? I just want to mention it here. It's just for introduction purpose. Cavitation. So in a lot of industry application, cavitation occurs. Okay, cavitation is a really 99% is a bad thing. I couldn't figure out any good application from cavitation. It might be, but I really couldn't figure out even one example. Okay, 99% it should be bad. Okay, very bad. Why cavitation is bad? What is a cavitation? Okay, usually in the liquid, in the pipe or whatever the device, it's not supposed to boil. Okay, you operate under room temperature. It's designed for it not to boil in most of the application. Okay, not to boil. So, but what happens if it boils? Okay, it won't, right? Room temperature, how can it boil? That's the problem here. There's a vapor pressure and the environmental pressure actually have some effect on the boiling process. I think you did the thermal, okay? What if the pressure is really low? Is the boiling temperature gonna change? For example, you boil water, try to boil a bottle of water on Mars, okay? We're gonna go to Mars, right? Maybe in what, 20 years? Human gonna land on Mars? I don't know. That's what Elon Musk says, right? So what if you're on the Mars, you want to boil water? Okay, do you need a 100 degrees Celsius temperature for it to boil, or like 270 or something Fahrenheit to let it boil? You probably only take a 15-degree temperature, it will start to boil. Okay, so why is that? Why the boiling temperature is lower on Mars So basically the pressure and the boiling temperature is also inversely proportional. Okay, inversely proportional. Okay, so your environment temperature, if it's environmental pressure is low, then your, I'm sorry, they're the proportional. It's not inversely proportional. What the heck am I writing? Just they're proportional. So if your boiling environmental pressure is low, your boiling temperature is also low. Okay, if your pressure is higher like Earth, you need more temperature for the liquid, same liquid to boil. Okay, they are proportional. Okay, so come back to the cavitation problem. Why does start to cavitate, start to boil? You know, it's bad. You know, you have bubble generated inside a full liquid pipe. Then the bubbles, you know, causing a lot of vibrations. You know, you don't have the space for the bubble. You know, you have phase change from liquid to gas. How many more space you need? Look at the density of liquid and the vapor. There's like 1,000 times of difference. Your density of vapor is 1,000 times smaller. So you need 1,000 times bigger space, volume, for the same amount of the material, right? Is that right? Okay, you don't have, it's a fully 100% filled pipe. Where is the volume? You don't have the volume. That's why you have very violent process in there. The vapor try to make a volume, but you don't have it. Okay, it causes vibration. It causes the damage of the facility, the equipment in a long run. Not even long run, in a short run, will damage it if cavitation happens. Okay, so the bubble, the boiling process is very bad. But you ask, hey, you know, they're not supposed to boil. My facility is under room temperature. What the heck is the water start to boil? One reason it will make it boil, pressure. You see the pressure. If the fluid experiences a very low pressure, then your boiling temperature for that same fluid decreases. It could decrease to the room temperature. Uh-oh, now the room temperature start to boil. Water start to boil at like 70 degrees Fahrenheit. Okay, under a very low pressure condition. Okay, sometimes people, designers forget about this. They design something, forget to ensure there's not very low pressure. Okay, low pressure is not good either in some part of the device. Okay, so that's the relationship, vapor pressure and the boiling temperature. Okay, keep in mind that will be related to the future topic of cavitation. Okay, so you have to avoid when you're doing design process. Now I'm just introducing here. We will talk about more detail later. When you design a fluid device, you make sure the pressure is not too low. Okay, in certain point, you need to. It's not necessary everywhere. You need to check, but you need to find your minimum pressure point in your design, in your device. Minimum pressure point. Make sure the minimum pressure point is not too low. Okay, otherwise cavitation might happen due to that. Okay, so that's another topic. I think these are the properties. You should have tables in the textbook about the relation vapor pressure, boiling temperature for liquid, common liquid. Okay, at the different pressure and the boiling point is different. Okay, not this book even. This book definitely has it, and also in the thermal books it always should be there. Okay. But that's related to the cavitation. Cavitation is an important topic, okay, for us to understand. Okay. Oh, I'm passing the time. Nobody remind me, huh? 10:47. Okay. I guess that's it for today. Everything good? Okay. Okay. Good. Good. Let me stop sharing, and so see you Thursday. Okay. Have a good rest of the day.
Thank you.
You're welcome.